In this video, we're gonna see the algorithm behind the simplest possible neural network. And then in another video, we're gonna see how to generalize it. So, the simplest possible neural network consists of one input and one output. We know the value for the input. Let's use the letter A for it. Stands for activation. We know that the input is connected to the output. And we also know the expected value. In other words, we have two known values, the input and the output. Our assumption is that the input and the output, they are connected using a linear rule, a linear function. Let's call x the weight that connects these two ends. The difference between the expected value and the value we calculated, we're gonna call it with the Greek letter delta. Our objective is to find the value of x that perfectly fits the given data. When the neural network starts, x is given a random value. And as such, we have a delta that can be very large or very small. And our objective is to find the way to improve the x. At this point, it is helpful for us to understand the following. Let's assume that we have the two x's. Here we have x. Here we have y. And our line, our function, can be seen as this, where a is the slope of this line here. This means that an x that lies, let's say, here is going to correspond to this y. And if, let's assume that this is the best value for y. In other words, this is y hat. What we are looking for is this value of x. Stop here and think. Since x was assigned completely randomly, it can fall in both sides of the best value. Let's call it x0. It can either be to the left, to the right, or to the left. If the randomly selected value for x is on the right, what we need is to come closer to the best value, which is the x0. If the random value was from the left side, we're going to move to the other direction. How much we're going to move? This is an arbitrary number. Let's call this step with the letter eta, the Greek letter eta. And let's say that every time we're going to move either to the left or to the right by h. In other words, the new x is going to be the old x minus h. Since h can be either positive or negative, it means that we are missing something from this equation here. What we are missing? We're missing a factor, let's call it g, which is going to take care of the sign. And if we are moving from right to the x, g is going to be positive because we want x to become smaller. And if we are moving to x0 from the left side, we want g to be negative because x must increase every time. For now, we are not sure what this is going to be. Let's try to understand. We said before that we define as delta the value y minus hat. It doesn't hurt the generality if we introduce a new variable and we're going to call it cost. And the cost, we can define it by this formula here. This is a completely arbitrary number. But, as we can see, it expresses the error in our calculation. On top of it, it is always positive because it is raised to the second power. We are doing so to cancel positives and negatives and always have a positive distance from the best line. We're gonna see why this 1/2 factor is also part of the cost. So this cost expresses the error that we have in our calculation. What we need to find is what is the relation between the cost and the y, the cost and the x. If we have a way to say that the cost is, for example, decreasing when x moves a little bit, increases a little bit, or vice versa, then we have a good way to define this question mark here. From this equation, it turns out that we can easily calculate the cost, the rate of the cost, over the y, over the calculated value. And this is nothing else than this. In the end of the video, I'm going to explain how this value is calculated if you need to. Note that this difference here, we have already named it as delta. So this is delta. We also know that y equals to a times x. This means that the partial derivative of y over x is a. If we combine these two equations and use the chain rule, we can easily see that the partial derivative of cost over x is the partial derivative of cost over y times the partial derivative of y over x. Note that these two, they cancel each other. Or, in other words, this is given by the product of delta times a. This means that the rate of change of cost in respect to the change of x is given by the multiplication of the delta times alpha. So, If we go to our original equation here and we substitute the question mark with delta times A, it means that we have the formula to improve our x and get it to become closer to the ideal here. Note that depending from what side you are approaching x0, the sign of this quantity here is gonna change, because x is gonna become larger or smaller from the expected value, depends where you're coming from. So in a neural network, the training phase is a repetition of this calculation, which is going to happen many different times back and forth until we reach a very good value for the x. When we move forward, we call this process feed forward, when we are calculating the delta, in other words. When we go backwards, meaning when we improve the x, we are doing the backpropagation process. The fact that we pick the delta c over delta x is an application of gradient descent. In our case, the gradient descent is the derivative of the cost. If we had multiple parameters, as we're going to see in the next video, we would have a gradient instead of a derivative. We're going to see this in more example, and we're going to understand it a little bit better. Another thing to keep in mind is that this eta hyperparameter is probably the most important parameter you have to tweak when you're training a neural network. Its size is going to make a big difference in both the accuracy and the speed of your calculations. To see this intuitively, let's consider a simple example. Let's say we have the example we saw before, where we have this line here, and the best value is this. Okay. Now, depending on the value of h, if it is very large or very small, as we are approaching it from both directions, we might miss it all the time. For example, from here we might go here, and then we're gonna go back, and then again the same. And if the h is not small enough, we will never get very close to the absolute, to the best value. And we're gonna see later of techniques that we use to mitigate the error that comes out of a very large eta. And of course, if the eta becomes very, very small, it might get the best answer or get very close to it, but we understand that the calculation is going to be very slow. In the next video, we're going to generalize this for multiple hidden layers. Thank you so much.